Hi, in this video I'll be talking about Bernoulli's equation, and Bernoulli's equation is similar to linear first order differential equation. They are almost the same. So I have already discussed linear first order differential equation, how to solve this type of equation with the help of the integrating factor. So Bernoulli's equation is another type. So we will discuss this one in this video. My name is Daniel, and this is Twitter Think. Please subscribe to this channel if you have not. So let's box on to what we have today. So if you have seen my video on the linear first order differential equation, we learned that the linear first order differential equation is of the form dy dx plus py equal to q. And I explained that the function p and q are two separate functions in terms of the variable x alone. So I also said that these functions, the variables that I am using to represent here, may change depending on the type of question you meet. It can be any other variable apart from p and q. And then the variable y has its first derivative here. So we say it's a linear first order differential equation. And we said that the solution of this type of equation, the linear first order differential, can be solved with the help of what we call the integrating factor. And we learned that the integrating factor is the exponential function to the power integral of what? P dx, depending on whatever variable is here. So you put the function here and you integrate. With the help of this integrating factor, you use it to multiply the equation to find your solution. Now, the Bernoulli's equation is very similar to this one. But the only difference here is that the function at the right side of the equation, which is this, has y to the power n. So when the function of the right hand side is multiplied by the variable y to the power n, where n is greater than 1, then we say this is a Bernoulli's equation. Now, to be able to solve the Bernoulli's equation, we need to reduce the whole equation back to a linear first order differential equation by getting rid of y to the power n on the right hand side of the equation. Once we are able to do that, we apply what we call the normal integration factor to integrate the function on the left hand side, and then we will be able to reduce the equation to a linear first order differential equation. And then with the help of the integrating factor, you can find the solution. So I have explained this in just few statements, but I'll tackle this question. Listen very carefully, and then I hope by the end of the day you will get the concept. So now, looking at the function dy dx plus py equal to qy to the power n, the first thing we need to do is to get rid of y to power n. So first, divide through by y to power n. The result becomes y minus n dy dx. I've already divided y to power n here, plus py times y to minus n equal to qy to power n dividing y to power n. So this will now take care of this. So this is giving us y minus n dy dx plus py dot y minus n equal to q. I'll come back here. So now let me explain how I was able to get this. So now this is our function. We are dividing through by y to power n. So this side y to power n, this side y to power n, this side y to power n. This will take care of this. Now this is division. I need to change it to linear. So when I change it to a linear function, then I will get that. So this is the same as dy dx dividing y to power n plus py dividing y to power n equal to q. So now you can reciprocate this side. So you have dy dx times 1 over y to power n plus py times 1 over y to power n equal to q. Now, when I change this to linear function, I'll get negative n. So this is dy dx times y minus n plus py times y minus n equal to q. So that was how come we are getting this. Now, note that I have y to power 1 here. So from indices, I can pick the base, one of the base, and then add the powers. So this side of the equation is giving us p y1 minus n, because 1 plus negative n is y minus n. So that is what we will have here. So when we move on, we have y negative n times dy dx plus py 1 minus n equal to q. Now let's label this one equation 1. Now all we are doing is that we want to change this equation 1 back to what we call the linear first order differential equation. Once we are able to convert that, then we can use the integrating factor to solve. Once you get to equation 1, you get to this side, we consider y to power 1 minus n alone, and we substitute a variable to represent it. So let's say something like, let z be equal to y to power 1 minus n. And then let's label this equation equation 2. Now your next step is to differentiate z equal to y 1 minus n using normal integration factor method. Now how do we do it? I will differentiate z with respect to x, and I'll differentiate the function y with respect to x. So this becomes dz dx equal to, now I am about to differentiate a function with the power n. Now let's assume that y is a function and with a power n. How do I do it? This result is going to give us 1 minus n, let's put this in bracket, y to the power minus n dy dx. So I have differentiated y, the function y, with respect to what? X. Let's label this one equation 3. Now, I am about to take you back and explain this side of the equation. Okay, let's assume we have a function y to power n. The differential of a function y to power n is equal to use n to multiply the function y, n minus 1. So if I have an example like a function y raised to the power 2, then the differential of this is going to give us 2y 2 minus 1, giving you what? 2y. Do you get it? Now the exponent that we have here was 1 minus n. So applying the same principle, let's see what we will get. So we have y to the power 1 minus n. Now when I differentiate this using the same principle here, then this is going to give us, use the exponent to multiply the function 1 minus n times the function y, 1 minus n, subtract 1 from the result, minus 1. Now this is going to give you 1 minus n, y to the power 1 minus n minus 1. Now watch carefully, this will now cancel this one. So we are left with 1 minus n, y to the power negative n. And I said that for normal integration factor method, I'll differentiate this one with respect to what? Y, or just add dy dx. Very simple. And this is equal to the derivative of the variable dz dx. So your next step is, now this 1 minus n that you have here, whatever function that you have here, you pick this function in this bracket, only 1 minus n. Don't forget this can be a number, because if I have n to be equal to, let's say 4, then 1 minus n is going to give me negative 3. Now watch very carefully. You use 1 minus n to multiply equation 1. And that is how you go about it. Every time you use the function at the power to multiply what? The equation 1. So now let's do that. So multiply equation 1 by 1 minus n. So let's go to equation 1 and do that. So we have 1 minus n times y minus n dy dx plus 1 minus n times py 1 minus n equal to q times 1 minus n. Now we label this one equation 4. So in our next step, we are coming to compare equation 4, equation 3, and equation 2. Now watch very carefully. Now you can see that this side of the equation, the left hand side, 1 minus n y minus n dy dx, is equal to equation 3. Watch very carefully. You can see that the same result we have here is the same result we have here. So we can replace this side of the equation by dz dx. Again, we go to the other side, plus 1 minus n py to the power 1 minus n. When you look at this very carefully, you can see part of this side of the equation is equal to equation 2. Why? Now when we go to equation 2, we said that let z be equal to y to the power 1 minus n. And we are also having y to the power 1 minus n at this side. So we can say that this side of the equation is equal to what? Z. I guess you got the concept. So your next step is to substitute equation 2 and equation 3 into equation 4. As simple as that. So we learned that this side of equation 4 is dz dx. So I'll substitute that. So I have dz dx plus 1 minus n p times z, because y to the power 1 minus n is the same as z, which is the same as the equation 2 we looked at from here, equation 2, and this side is equation 3. Now we equate this to this right hand side of the equation, q into 1 minus n. So if you look at this very carefully, you can see that this equation is now a linear first order differential equation. Now let's compare this and see. We have the derivative function in terms of y, the variable y, the function q, and the function p. And when we come to this side, we have the derivative function in the terms of the variable z. We have the z variable, and we have the function 1 minus np, the function q 1 minus n. Now remember that the bracket we have here is 1 minus n. N is a number. This number should not make the function 0. So when we substitute this number here, it will multiply the function q and it becomes a whole function on its own. When we substitute n here, it becomes a function and it multiplies the what? The function p. So this is now a linear first order differential equation that can be solved using the integrating factor e to the power integral of what? P dx, or integral of 1 minus n p dx. So this is the proving. I don't need to continue this part of the equation because we have already discussed first order linear differential equation. So finally, when you reach this side of the equation, for this type of question, you are done. You just write the statement like, this is now a first order differential equation for z, the variable z, which can be solved with the integrating factor r of x equal to e integral of p dx, because the question said that using the integrating factor that. So you write this last statement to complete the calculation. So anytime the Bernolli'S equation come in this form, as in the proving form, after proving, when you get to the linear first order differential equation, you just write a statement like this in your own way. So this is the end of this video. Now in my next video, I am going to talk about different examples of the Bernolli'S equation so that we can substitute a function for n and see how we can solve it. But for these type of questions, when we get here, we need to continue the calculation until we have been able to integrate the linear first order differential equation. So this is Daniel. Thank you for joining me, and I'll see you in the next one.